Hello, everybody. I'm Dr. Shafiq, and I would like to welcome all of you in this video session. Today, we'll review Chapter 6, which is Straight Footing Foundation. Okay, let me share my screen with you. Tarzaghi is the first scientist who introduced the idea of bearing capacity. So he was taking a stiff foundation and put that one on top of the soil in a plexiglass box. Okay. And then he started increasing load on that foundation until it failed. And he was observing that how this foundation is failing. Then he tried to show that one here, and you can see that he separated the failure zone. Here is your failure zone into three different parts. First, there is a triangular ACD area, and then he saw two radial shear zone, ADF and CDE. And then he also saw these two triangular Rankine passive zone. Okay. And then he, from this diagram, he tried to solve the equation for equilibrium or equation for statics. Okay. And then he proposed that equation here, QU equal to C prime NCQ NQ 0.5 gamma B N gamma. In this equation, QU is the ultimate bearing capacity, C prime is the cohesion, Q is the actually effective stress at the foundation level, which is gamma DF. And gamma is unit weight of soil, DF is the depth of foundation, and NC, NQ, and N gamma is the bearing capacity factors. He also proposed, because he did his original, equation for the street foundation, then he also proposed the bearing capacity for square and circular foundation. Now, in this equation, you can see there is like three different parts here. This first part, we call that one cohesion part. The second part we call the surcharge part, and the third part we call that one soil weight part. Okay, now here is your equation for square foundation, which is 1.3 C prime NC Q NQ plus 0.4 gamma B N gamma, and circular foundation is 1.3 C prime NC Q NQ plus 0.3 gamma B N gamma. But the problem is like the foundation can also be rectangle or other shape, which is not covered in this equation. And also soil could be, also foundation could be such that there is inclined load, and this equation cannot handle that one. So basically there is a general equation which was upgraded by Meyerhoff, and he proposed a new general equation. So here is the general equation. You can see is ultimate bearing capacity is C prime NC, FCS, FCD, FCI, QNQ, FCS, QS, FQI, half gamma B N gamma, F gamma S, F gamma D, and F gamma I. These are actually, he just added some factors here, like these are called like CS, QS, gamma S. These are the shape factor. So this one will be changed as the footing size is going to change. Similarly, he added FCD, FQD, and F gamma D, which we call depth factor. And this one also changes with the depth of the foundation, as well as the phi of the friction angle of the soil. Similarly, he added like FCI, FQI, and F gamma I. These are actually load inclination factor. So if there is any load inclined load, then basically you have to find out these factors. Now, if your soil is stiff soil, then all of your shape factor would be actually 1. Similarly, if you don't have an inclined load, then basically your inclination factor would be also 1. Now, let's see that how the bearing capacity factors actually a little bit different for Meyerhoff's equation than the actual Tarzaghi equation. So you can find out this NC, NQ, and N gamma from this equation, and you can see actually your NC, NQ, and gamma is only the function of phi prime, okay? The bearing capacity factors is only the function of phi prime, which are shown in table 6.2, because we usually don't want to use this equation because there is a chance for calculating like them. So it's much easier to use the table 6.2. You can see if you know your phi prime, then basically you can find out your NC, NQ, and N gamma. Okay. One thing you can just notice here that for clay soil, your phi would be 0 in that situation. Your NC equal to 5.14, NQ equal to 1, and N gamma equal to 0. Okay. Now here is your shape factor. You can see your shape factor FCS equal to 1 plus B by L, NQ by NC. FQS equal to 1 plus B by L tan phi prime, and F gamma S equal to 1 minus 0.4 B by L. So your shape factors are the function of your BL as well as your phi. Now you can also observe here that for square foundation, your B by L equal to 1, right? So B by L equal to 1. So in that situation, actually for any particular soil which has a specific phi, your FCS and FQS would be maximum for actually square foundation, and minimum if gamma S would be minimum for square foundation. Okay. On the other hand, you can also see if your shape of the footing is like continuous, means like a strip footing, then basically you will see that your B by L would be very, very small in that situation. FCS, FQS, and N gamma S is almost close to 1. Okay. Here is your depth factor. Okay, depth factor, like 2 different type of equations you have to use. One is for df by b equal to less than 1, and the other one is df by b is greater than 1. Now, if your soil is clay soil, then you use these 3 equations here. If your soil is CFE soil or granular soil, then basically you use this equation. Okay, so you can see also the depth factor, the function of the depth of the foundation df, b, and phi prime of the soil. Okay, here is your inclination factor, FCI equal to FQI equal to 1 minus beta by 90 square. So you can see beta is the inclination angle which makes with the vertical. Okay, so once you know your beta, you can just use these equations to find out your inclination factors. If beta is equal to 0, means like the load is vertical, then basically all those factors will be equal to 1. So here is the example for this general equation, how to find out your QE for using the Meyerhoff's equation. If you just take a look, this might help you to understand that one. I'm not going to discuss that one because I already discussed that one in your actual bearing capacity presentation. Okay. there are two things that has pronounced effect on your bearing capacity. One is the water table, the other one is the eccentricity. Okay, so if you see the effect of water table, which can affect that Q and also the gamma. Okay, now how this one would be affected, I'm just trying to show that one to you. Let's say this is a rectangle, footing. So the location of concern, like where we look at, is actually like most important thing is like, hey, what type of soil we have, like at a distance from the bottom of the foundation to a depth of B here. B is the width of the footing. Okay. We don't care that much about like, hey, whether what kind of soil here or what is the condition of water and other things beyond that distance B from the bottom of the foundation. Now, if you have water table which is below that line here, then basically you don't have any impact on your QU for that, water table here. So that's why we call that one case 3. I'm showing that one, there is no effect for that. So you don't have to change your Q or gamma for this case 3. Okay, so case 3 is when your water is below the line drawn from the bottom of the foundation to a distance B. Okay, now let's see the other cases. So this is case 1, which means like your water table is in between DF, okay, the bottom of the foundation, and this is your ground level. If the water is in between here and here, then we call that one case 1. In that situation, your Q at the bottom of the foundation, you can see would be equal to D1 gamma plus D2 gamma set, right? So that's what we are trying to see. Like your Q has changed a little bit because this is the effective stress. So you have to, take the weight of water from there to find out the effective stress. Okay. And then what is the, gamma here? You will see that when this one is submerged, then basically we use submerged unit weight, which is actually gamma sat minus gamma W. Okay. That's your case 1. So your case 1, actually your Q and gamma will be changed. Q will be equal to this one and gamma will be equal to your gamma submerged. Now let's see, like if you have water table not in between here and here, but in between the bottom of the foundation and a distance B from the bottom to the foundation. Okay, so actually your water table you can see in between here and here. Okay, so in that situation, what would be your Q at this point? You can see since the water table is below that point here, so your Q would be just gamma DF. Okay, doesn't have any impact there. But what about the, like gamma below the foundation? You can see from here to here, your gamma is just gamma, and from here to here, actually, your gamma is your submerged gamma, right? So we just try to take the weighted average of these two. So this distance from here to here is D, and from this distance from here to here is B minus D, okay? So I'm just taking the weighted average of these two gammas, and then I'm getting this gamma like this figure here, okay? So for case 2, actually your Q would be just gamma DF, and this gamma will be replaced by this one here. Okay, now let's move forward. Eccentrically loaded foundation. You can see here in that case, the column is here, but the load is actually coming here. Okay, so it's not aligned. So it's creating some moment. That's called eccentricity. Similarly, here you can see this is the, like the support here, and the load is coming here. So this is your eccentricity, like the load is actually not aligned with the reaction here. Okay. Similarly, this is the figure for a footing, and you can see your reaction would be along that line, but the load is at a distance E from there. So that's creating some moment. So if it creates any moment there, then basically this is eccentric foundation. Now, let's check that what we understand like about the eccentricity here is this is an eccentric footing. Okay, so you can see this is just working at the middle of the column, but the column is not at the middle of the footing. So if you see here that this is basically the center of the reaction, because this is total 5 feet. So this one from here to here is 2.5 feet. But you can see the load is actually working 2 feet from here. So the distance from here to here, that's actually your E, which is basically 0.5 feet. Okay, so basically this is eccentric footing, right? Now let's see this case here. There's inclination. This one is working along that line here. But the thing is like, this is basically the reaction. This is the middle of the foundation. If there is even eccentricity, but this one is passing through the center of the footing, then basically this is not eccentric. Okay, this one is inclined force, but not eccentric. How about this one? When they show you like the force as well as moment, this means like you already have eccentricity and they already gave that information to you. Okay. Now let's see how we handle like this kind of situation. So if you see here that this is not, the force is not working along the center here, it's working at a distance E and here. So this one will try to push more weight along this side than this side. And we can just show that one as your Q equal to Q by A. Q is the load divided by the area, plus minus MC over I. Okay. M is the moment that will create, which is Q into E. C is the distance actually from here to here, B by 2, and I is the moment of inertia along that line here, which is actually LB cubed by 12. So if I show that one here, that area equal to B into L, Q equal to Q, and then moment equal to Q into E, C equal to B by 2 from here to here, and your I along that axis is LB cubed by 12, then basically if we plug that value in this equation, then we get Q max equal to Q by BL, BL is the area, plus 6M by B square L. Similarly, we get our Q mean equal to Q divided by BL minus 6M divided by B square by L. Okay. We are not going to use this information to solve that problem, but this is just for your understanding that actually what's happening here. Now, if you see here that what would be your maximum and minimum value here, when you plug that value M equal to QE, so you get that one here, okay? Now you can see when your Q minimum would be 0, then if you solve that equation that Q min equal to 0, then you will find out that your E is basically equal to B by 6. Okay, so when E equal to B by 6, then basically one side you will get 0 reaction. if your E is greater than B by E, then basically you will see for some part, actually soil is not taking any load. Okay, and maybe sometimes it can come out from there. Okay, one side is going down, the other side is coming up. On the other hand, if your E is less than B by 6, then basically you will see a maximum pressure in one side and minimum pressure at the other side. We usually try to design all of our footing so that like your E is less than B by 6. Okay. Now let's see that how usually we handle this kind of situation. So the most common one for one-way eccentricity is the Meyerhoff's effective area method. Okay, so if you have like a footing, something like that, and your cube is here, which is making an eccentricity here, the load is working at this point, so you can understand since this one is working this way, so this one will have higher pressure and this one will have lower pressure. Okay, so what we usually do, that since the eccentricity is in the B direction, this is your B direction, so our effective B would be equal to B minus 2E, and effective L would be equal to just L. Now, your eccentricity could be in the L direction too. Okay, here is your L direction, this is your B. In that situation, your B prime would be your effective width, which is equal to your B, but your effective length would be L minus 2E. Okay, and after adjusting that, subtracting that 2E either from B or from L, then we have to check again that which one is bigger, either L prime or B prime, and you have to make sure that your L prime is always bigger than B prime. That's the assumption we use in all foundation engineering problem. Okay. Now the following terms of the bearing capacity will be changed because of the one-way or two-way eccentricity. Actually, only the shape factors and your B. Once you find out your L prime and B prime, then your shape factors will be determined based on L prime and B prime. However, your depth factor and inclination factor, actually inclination factor doesn't need any B or L. So basically your depth factor will be like evaluated based on the actual B and L. Okay, so only the shape factors will be affected. At the same time, this B will be replaced by B prime all the time. Okay, so we are just saying the third part, this B will be replaced by B prime. Okay, now you can see your total, like ultimate load that can carry is equal to QU multiplied by the area. So your effective area is basically B prime and L prime. And you can find out if you know your factor of safety, then this is basically your Q allowable is basically QU divided by your factor of safety. Okay. Now there is an example here that you can see this is a square foundation, 1.5 meter and 1.5 meter. And your eccentricity is 0.1 meter here. So you can see your B and L equal to 1.5 and L is also 1.5. So your B prime would be B minus 2E. So 1.5 minus 2 into 0.1. So this is 1.3. And your L prime is 1.5. Now I have to again change that after subtracting the 2E, whether my B prime and L prime within our B prime and L prime must be bigger than my B prime. So here I check that yes, L prime is 1.5 and B prime is 1.3. So L prime is bigger than B prime. So I'm fine. Now I have to, what I have to do, I have to use that B prime and L prime to find out my shape factors. On the other hand, I'll find out my depth factors using the actual B and L. Okay, and then the third part of the equation, B will be replaced by B prime. Okay, so then we are done. Let's talk about a little bit about two-way eccentricity. This one is a little bit complex. Okay, not the way like we can just take like the 2E from B or L. Okay, we cannot do this way. That would be wrong. Okay, so here, if we have like 2A eccentricity, then basically you can see the only terms that will be affected is same as one-way eccentricity, FCS, FQS, if gamma is means like all shape factors. Depth factor will be determined based on the original B and L. Okay, and this B will be replaced with your B prime. The only thing we have to just find out, hey, what would be our B prime and L prime, which is a little bit complex than one-way eccentricity. When we find out that B, L prime and B prime, that basically it's not that difficult. Now, to find out, actually, we have to have several cases based on your EL by L and EB by B, whether this one is equal to or less than 1/6 or bigger than 1/6. Okay, so when your EL by L equal to 1/6 and EB by B equal to 1/6, both of them, then basically this one will just go through this line here. Okay, here you can see your EL by L is actually greater than 1/6 and EB by B is greater than 1/6. So this line has moved here. If you increase that one more and more, this line will go to the right direction. Okay. Now, how do you find out the effective area? That's basically my effective area. So if this is B1 and this is L1, then this area would be half into B1 into L1, right? Half into B1 into L1, where B1 is equal to this equation, B into 1.5 minus 3EB by B, and L1 equal to L into 1.5 minus 3EL by L. And then from this equation, I'll just use that one and find out my effective area. Once I get my effective area, then I can find out my L prime is the larger of B1 and L1, and then B prime would be effective area divided by L prime. So this is the case one. Actually, we don't need any diagram or any like figure to find out this information. We can just use these two equations to find out our B1 and L1. Okay, now let's move forward. Like case number 2, when EL by L is greater than or equal to 1/6 and EB by B is less than or equal to 1/6. In that situation, this is the figure. So you can see this is basically a trapezoid. So the area would be this plus this divided by 2 multiplied by this, right? So that's actually L1 plus L2 divided by 2 multiplied by B. Okay, that's your effective area. Now your effective length, L prime, is the larger of L1 and L2, and your B prime would be A prime divided by L prime. Okay, divided by L prime. So L prime could be L1 or L2, which one is bigger. Okay, now you can see this is for case 2. There is basically a diagram given to determine your L1 and L2. Okay. For case 1, actually, you can do that when using your equation. For case 2, actually, you have to use this chart here. Okay. In this chart, you see the EL by L, and this is EB by B. From this side, you can find out L1 by L, and this side, you can find out your L2 by L. Okay, so this is your L1 by L or L2 by L. I'll show one example that how you can find that out. Okay, now let's move forward. For case 3, when EL by L and is less than 1/6 and EB by B is greater than or equal to 1/6. So that's the effective area. Now you can see again, this is a trapezoid. This is B2 and this is B1. So the area of that trapezoid would be B1 plus B2 divided by 2 multiplied by L. Okay, so B1 plus B2 by 2 into L. Now, effective length L prime is equal to L, and your B prime is equal to your effective area divided by your L prime. Okay. Here is the figure to determine your B1 and B2. So once again, you can see it's a function of your EB by B and EL by L. So this dotted line here, if you go to the right, that's for your B1 by B, and anything from here to here, that's actually your B2 by B. So these are either B1 by B or B2 by B. That depends on like your EL by L and EB by B. Okay. Now case 4, when EL by L and EB by B is equal to 1/6, or both of them are less than 1/6. Okay. In that situation, their effective area is much bigger now. And once again, you can see this one, you can just divide that one into 2 areas, like line here. So this is one area, and there is another trapezoid here. For that rectangle area, this one is B into L2. That's B into L2. And for this trapezoidal area, that would be this distance into this distance divided by 2 multiplied by from the distance from here to here, right? So this distance from here to here is basically L minus L2. So L minus L2, and then the average of B2 plus B. So that's basically your total area. So your effective length L prime is equal to your L, and your B prime is equal to your effective area divided by L prime. Okay. Now this one is your case 4, when your EL by L is 1/6 and EB by B equal to 1/6. But how you can find out your B2 and L2, that's what this one is given here. And once again, this is your EB by B, and this is your EL by L. This one for obtaining B2 by B, and this one is to obtain L2 by L. Okay, so ones are like these equation, like these lines. The other are like these lines. Okay. Now, case 5 for circular foundation under eccentric loading. The eccentricity is always one way for circular section. So determine the effective area and effective width from the table 610 here. You can see if you know your ER by R. So ER is the eccentricity, R is the radius of the circular section. And from there, if you know your ER by, then you can find out your A prime by R square and your B prime by R. So you can find out your A prime and B prime. So your L prime is A prime divided by B prime. Okay. So there is an example here. You can see this one is saying that this one B by L is 1.2 and 1.8 meter. Here EB equal to 0.12 meter and EL equal to 0.36 meter. So what you have to do first is just find out your EB by B and EL by L. So you can see your EL by L equal to 0.36 divided by 1.8. That's actually 0.2, which is greater than 0.17, means like 1/6. 1/6 is 0.167. So you see your EL by L is greater than 1/6, and EB by B is less than 1/6, which is 0.1. So you just match that one, that EL by L is greater than 1/6 and EB by B is less than 1/6, which is case 2. Okay, so you come to case 2 and use this chart here, and you have to have your EL by L, which is 0.2, and EB by B equal to 0.1. So EL by L equal to 0.2. So I have to get, like, here is 0.2. I can draw a line from this and try to see that where this one will intersect with EB by B equal to 0.1. So EB by B equal to 0.1 here. So if I take that data from here, then basically this one for obtaining L2 by L. So L2 by L is kind of 0.2. So from the figure, L2 by 2 equal to 0.2, or L2 equal to 0.2 L equal to 0.2 into 1.8, which is equal to 0.36 meter. And to find out by L1 by L, which is from this side, I have to see where is 0.1. This is the line for 0.1. So this one intersected here. So I'll draw a point here, and this one is, let's say, 0.83. So L1 by L equal to 0.83, or L1 equal to 0.83 L, which is 0.83 into 1.8. So this one is 1.5. So my effective area would be L1 plus L2 divided by 2 multiplied by B. Once I know my effective area, then basically I can find out my L prime and B prime. Once I get my L prime and B prime, then basically I have to use that one to find out the shape factors. On the other hand, my depth factor will be determined from the actual B and L, and then I have to plug that one in the equation, and my B has to be replaced. The B in the third term of the bearing capacity equation will be replaced by B prime. Then I can get the answer directly from there. Anyway, that's basically our review. If you have any question, please let me know. I'll just, stop it here. And once again, thank you for your attention.